Hey guys, it's Fusheng here and welcome back to another video. Today I will be doing a multi-class image classification, but we are not going to predict the labels of our image. Instead, we are going to predict the values of our JSON files. So you'll understand what I'm doing in this entire notebook if you watch till the end. So without further ado, let's get started. So as you can see in this dataset right here, we're using the same dataset as the previous video. So if you have downloaded it, you do not have to download it again. So let's get started. So first of all, we are going to use the donkey car categorical method, which uses linear bin and unbin. So what it does is that these functions, linear bin and unbin, they actually one-hot encode our values, and from there we are able to get the predictions after we train our model. So these functions mainly help us to encode our values. So let's move on to loading the dataset. So we're going to create some list right here, and we're going to append the x and y values into the list. And as you can see, we have this encoded category right here where we'll append the function which we have called of x. So we are going to linear bin x, and what linear bin x does is that it will encode, one-hot encode all values of x as it iterates through this for loop right here. And then we will do the same for linear bin y, which is the one-hot encoding of the throttle. And once we have done that, we will run an if statement to get the image tensors. And what we are going to do is we're going to append the image tensors inside this list. And finally, we will output all of these predictions, all of these outputs right here. So we can see this list right here. This is the angle value, and then we're going to one-hot encode it to get it into one-hot encoding right here. And then these are our image tensors in array format. And then if we scroll down, we will be able to see that these are our throttle values and our one-hot encoded throttle values. So once we've done that, we are going to convert our image and categories into array. So we're just going to create a variable called array image list, and we're going to use numpy.array bracket image list, and it is simple as that. So if we print out the shape right here, we can see that our image is correct as well as our labels. So we have 15 categories for the angle and 20 categories for the throttle. So after that, we are going to create XYZ variables, and then we are going to train test split them. So after we train test split them, we are going to train the model. So this is actually a model from the donkey car model architecture. So I've just copied and pasted this, and this is a functional API model, which is different from the sequential model because the sequential model only accepts one input and one output. However, the functional API model can accept multiple outputs. So we're defining the input shape and the optimizer as well as the dropout rate. Then we're going to specify the image input and the layers which we are going to add inside. And once we have done that, we're going to come here to the flatten dense dropout layer. So this is our fully connected layer right here. And as you can see for this dense layer right here, it is unique to its angle out value, and also for the dense 50, it is also unique to its throttle output. So it is not necessary that you use the total number of convolutions, feature input, and add them up together. However, you can use a reasonable amount, not too much, not too less, because if you use too less or too much, then there are too many nodes which are connected to each, which have to be connected from layer to layer, and then that will cause the model to not predict well, to have a difficult time to learn and connect these nodes together. And once you have done that, here is why there are multiple outputs for a functional API model. So I have a dense layer which I can call it angle output, and in this layer we have 15 outputs. However, we also have a throttle output here which has a dense layer of 20. So we are going to output 20 categories inside here. So these are multiple outputs. So once we have done that, we are going to specify the model input and the model output, and after that we will compile the model. So it is important to specify the loss for the outputs right here. Then we're going to specify the optimizer and the matrix, and we're going to plot the summary of it. So we're going to get the parameters right here, and now we can start to use the learning rate. And what learning rate does is that it will reduce the learning rate of the specified matrix and improve it in the next epoch. So we have set the patience to 1. So if it does not learn after if it does not improve after 1 epoch, then in the next epoch it will reduce the learning rate in order to improve that metric. So right now we will train on our dataset. So how do you do this? We're going to specify the epoch batch size and steps. Then over here we're going to use model.fit, and once we use model.fit, we're going to specify the x and y. So we're going to use xtrain for the x because we have to train on our image tensors, and for our y, which are our labels, we are going to specify them in an array of xtrain and ztrain. And then we're going to specify the epoch, the validation data, and for the validation data we're going to use xtrain, xtest, ytest, ztest. So it has to be in the same format, and then we're going to use callbacks. Oh yeah, you don't need steps at all. So let's take a look at the training right now. So we're going to train on this amount of samples and validate on this amount of samples. So for one epoch, it's training on this amount of samples, and it takes around 100 seconds for my PC. And as we look at the loss and angle loss, we can see that the numbers are quite high, but as we continue to train it, it actually reduces. And as you can see, the learning rate actually the learning rate plateau actually is over here, and it helps to improve the metric of it. So if we compare epoch 38 to 39 to 28 to 29, it actually improves. Then let's just take all the way down over here. So finally, we're going to look at our metrics, and it seems to be pretty good. So once you have gotten that, we're going to plot our graph. So when we plot our graph, this is how a perfect curve should look. And this goes for the validation loss as well, except from epoch 20 right here, it just started to stop going down and it just overfits. And however, if we look at the throttle validation, it seems to be underfitting severely. And it is also the same for the accuracy. The accuracy, it's at 1, so it's not really improving. So basically, this means that it has achieved the highest accuracy it can get, and that our training label for our validation training is simple for the throttle. So for the throttle, it is easy to learn. However, it is not so easy for the angle. So now that we have trained our model, we're going to save it, and then we're going to load it so we do not have to retrain our model again next time. So we're going to use model.predict, and we're going to predict on the image list, the array image list, which are the 2D tensors. So we're going to predict on them, and we have 2 arrays. So we have prediction 0 and prediction 1. So once we have done that, we're going to see that all the categories are all very different, and these are all numbers. So right now, from these numbers here, as you can see, so this is for the angle and this is for the throttle, because 0 is angle and 1 is throttle. So right now we are going to plot the graph. So we are going to put the predicted angle with the original angle to see how well it is going to predict, so we can actually compare one another. So we're just going to plot the predicted angle with the angle results right here. And as you can see, in the blue line we have the predicted angle, and in the orange line we have the angle results. So it looks pretty good, except for some minor predictions which are wrong. However, I think overall it is quite good. So let's take a closer look at our predictions. So if we actually compare both of this, I think that it is pretty much on par with one another. So I would say that it is 90% accurate. So next thing is we are going to plot the prediction of the throttle with the original throttle. So of course we have to linear unbin. So we are going to linear unbin in both the predicted angle and the throttle. So what this linear unbin does is that it converts the one hot encoded angle and one hot encoded throttle value into its normal value. So right now if we take a look at this right here, in the orange one we have the predicted throttle and the blue one we have the throttle result. So we can see that they are actually on point. However, the predicted throttle is not predicting the negative throttle prediction right here. So there's a gap. However, I think that it is pretty good. So looking at this, we can see that it only predicts until 0. However, the original one is 0.4 to minus 0.4. And with that, we can plot the graph of everything. So when we plot everything together, we can see that it is kind of small, but I'm not sure if you can see it. Well, it is kind of difficult to see, but this is most probably the ideal when we compare everything together. So we can see the red line and the orange line as well as the green line and the slight blue line. So overall, we have gotten our predictions, and I think they are well predicted. So I hope you have learned something from this tutorial where we predict the JSON file values and compare it with the original values. And with that, I would like to end my lesson, and I'll see you guys again next time.